No one's watching. No one's watching live. That's okay. Like all this right now, me eating this fruit, this could take like however many minutes. And then in the post-production, I'm gonna cut it down and it'll be like nothing happened. Salut tout le monde. Welcome back. It's me, Anthony, obviously. Here we are again with, you probably thought I gave up, but we're back with another differential geometry reading stream. It was, I don't know, the end of summer, so I tried to go outside and stuff and, you know, hang out with people, whatnot. This is what I'm going to say. This is from Timaeus, the Platonic dialogue. Maybe you could call it a Socratic dialogue that I've referred back to now several times, more than any of the other Platonic dialogues throughout the course of these reading streams. Take that for what you will. But from Timaeus, it says, "There is one protection against disproportion. Be healthy and well balanced. And therefore, the mathematician must allow his body to have due exercise. And he who is careful to fashion the body should cultivate music and all philosophy." That's not totally an answer of where I've been, because if you guys know me, I'm always about that exercise grind, trying to get the strength gains, trying to get the mass aesthetic gains, trying to put those gains to a use in an actual athletic skill, sport of grappling, because no, bodybuilding is not a sport. And powerlifting, when you really think about it, it really is just, you know, you're gonna do one rep. That's what it's building up to, picking something up and putting something down. And after a while, that does get boring, you've got to admit, you know? Powerlifting, going to the gym, to me, yeah, okay, obviously I'm not genetically Chris Bumstead or Michael B. Jordan when I take my shirt off. I do disdain, however, people who say, oh, I have bad genetics, therefore I'm not going to lift. I hate those people, don't get me wrong. But at the end of the day, lifting weights and staying in shape is kind of just like wiping your own ass. It's just like, you should just kind of do it. Kind of like someone who is all up in your face talking with bad breath when you can tell that it's been a while since they've brushed their teeth. You question whether they know how to brush their teeth, right? That's kind of how it is when someone comes up to me and, you know, you could be this mathematician guy or whatever, but it's like, if I can tell that you don't know your way around lifting weights, all this kind of stuff, that's the point. Going back to Timaeus, Socrates, that's, you know, almost like 3,000 years ago, if you want to think of it that way, because like 800 BC to now, it's basically like on the scale of 3,000 years. And even back then, they were saying, oh, if you're some dork, you need to maybe think about lifting weights more. Anyways, okay, what was I saying? So where I left off now, like a few months ago, also, I will say it was getting a little bit formulaic. Not that there's anything wrong with sticking to a format, but when things were starting to get a little more cookie cutter with my execution and delivery of these, that's when I was like, okay, I feel like my best videos are always the ones that I put like a little more effort into. Like, it's definitely possible for me to just like crank out videos or whatever, but the better ones are always the ones that have a little more effort put into them, which is like, go figure, right? So I also was like, well, I also, you know, I don't want to rush through this book, because me reading this book and recording that and all that stuff is what's taken my channel to be more popular than it's ever been in the last 7 years. So why would I want to waste the opportunities that reading each one of these sections provides, right? So I was like, okay, I'm going to take a step back. I'm going to try to enjoy the end of summer, because, I mean, another thing too is that these videos take like the entire weekend sometimes to film, edit, and upload. And when I say upload, I also mean, you know, making the thumbnail, putting the description together, and, you know, all of that stuff. That is like its own separate process in addition to the filming and the editing, which is also, you know, if I'm being honest, talking about the better videos that have a little more effort put in, that means preparation. So reading through or even skimming through the section beforehand so that I can pick out the theorems or expressions that get referenced in line and being able to read those seamlessly when I go through and do the actual reading. All that takes time. And so it's like, well, if I'm working at my normal day job Monday through Friday and then I do this Saturday to Sunday, I was getting a little bit burnt out from it, especially with what I was saying about it being really mechanical and stuff. But anyways, okay, another thing I want to say is, okay, two things. I initially got this book about 10 years ago, okay? And yes, okay, I got my undergraduate degree in math, but my real interest in a lot of this stuff is motivated by understanding physics, right? Because if you just read math, it's like, okay, great, you have a good memory for all these definitions, and there's all this, you know, fancy stuff that you could have going on, and how it seems so profound and intellectually deep and stuff. But like at the end of the day, if there's no good application or anything like that, you're just jerking yourself off. Let's be real, okay? So nothing wrong with that, but just for me, I don't want to be just jerking off all the time. You know what I'm saying? So differential geometry, the reason for learning this, I've mentioned this, is to better understand things in physics like general relativity, okay? You could say that manifold theory in general is kind of like the mathematical language for general relativity. So it's like, okay, I mentioned this other book before and kind of skimmed it in another episode where I was like, oh, I'm going to review one of the chapters that I had finished reading at the time. Okay, general relativity, Wald. The first chapter is the introduction, which lays out this conceptual framework, which is like what Einstein basically did to go beyond Newton's classical model of space-time and gravitation, okay? But this introduction chapter in Wald's book, okay, it introduces all this, but it basically does not bring up any of the math, okay? Then it goes through 2 chapters of just like getting waterboarded with math, manifolds, tensor fields, curvature, geodesics. Okay, I did a geodesics read the entire chapter in one go episode 2 episodes ago. If you thought that was fast, imagine what's in this freaking book, okay? Just saying. But then, okay, so we have a loosey-goosey conceptual introduction, 2 waterboard, just get, you know, slapped on each sides of the face real quick with some math. And then chapter 4 is just basically doing everything in the introduction, but now we're going to go through the math, okay? So I'm like, well, reading this differential geometry book, if you were really good, then you could read the introduction to general relativity. You could just get that conceptual part, and then you should sit down and be like, okay, how would I take those concepts and then dress it up in what you should already know hypothetically from being like a mathematician expert or whatever kind of guy, right? That would be the real test. So I'm like, okay, that's chill. I'm not in a rush to read general relativity, so. Right, but you kind of get the idea. And so anyways, yeah, also so that was like 10 years ago. And so now I'm finally getting through this. Another thing about 10 years ago, I mentioned this like I keep mentioning, going back to things over and over, is that I was reading Gravity's Rainbow, and I finally finished that book, which I had tried to read multiple times. I'd get a few hundred pages through, and then I'd fail. It's like an 800-page book, so if you get like 200 pages through, you're just kind of like not really getting into it, let's be honest. But I finally finished it, right? And then I got hit with this wave of like, oh my God, I just don't want to read really right now. It was almost like a deep subconscious tension from not having checked that book off my list. It's finally like, oh my God, now I can, go outside and enjoy summer a little bit. And so I haven't converged upon like another main book that I'm reading now in the time since. I've read things like going through this book, Mauve. It's about a chemist named William Perkin who basically developed this chemical method for producing color of dye. It's called mauve. It's like a shade of purple, which previous to his discovery, invention of the chemical production method, the previous method for creating that color of dye was extremely laborious and expensive, namely that you'd have to extract the dye out of like crushing hundreds or thousands of these little freaking snails that only grow in this one part of the Mediterranean and all this kind of stuff. And then he was able to use byproducts, waste at the time essentially, of petroleum processes. So going from coal to petroleum, waste at the time in England was just piling up of all this stuff, and he found a way to make that into a more cost-effective alternative for this really expensive dye. And it turns out that that similar process would have huge, far-reaching implications for chemistry, okay? What does that have to do with Gravity's Rainbow? Well, Thomas Pynchon writing that book, it'd be like one sentence is like a rabbit hole of like a PhD thesis of information. And for Thomas Pynchon to have written that book in the 70s, not having access to like computers and stuff that are connected to the internet where you could just Google search this stuff and then, have your typewriter typing up Gravity's Rainbow on the side. Incredible that he was able to do that in that time. But, right, so I've just kind of been like reading fragmentary other stuff related to Gravity's Rainbow to kind of tie those loose ends up. I've sort of settled on reading The Master and His Emissary by Iain McGilchrist, because one of the themes of things I keep reading about just in general is like neuroscience, brain morphology, and I've always been curious about the whole hemisphere hypothesis of understanding the structure and function of the brain from a vantage point that emphasizes the hemispheric differentiation of the brain, and kind of the intuition that there is something to that, particularly in how our hemispheres are differentiated in humans, that then contributes to what people would call the unique human experience. But of course, a lot of those questions that this hemisphere hypothesis kind of has baking under the hood are really difficult to answer. Like, for instance, they're asking questions about the evolution of not only human brains, but the development of human consciousness and experience over centuries, millennia, which we have scant fossil evidence about the morphology of the outside of brains to begin with, because if you think about it, brains themselves, hard to fossilize. Fossils in themselves, super rare. What are you going to have the most of in this ultra rare category? Fossils of skulls where you can see the imprint of the brain in the skull. That's like the best you could do, maybe. And then that doesn't say anything about like what was that individual's behavior like? What was, behavior looking at as like another person? What was then their subjective internal conscious experience, if it was different or the same from what modern people are like now? And then it asks questions implicit within that. Well, if you get all these people who are living today in September of 2024, you get a bunch of people from around the world all together. Who's to say what kind of similarities or equal footing you could put those people's mental, cognitive, conscious experiences on, right? So there's all kinds of problems with, you could say, the evidence aspect, right? But at the same time, you do have things like language and writing, which you can't necessarily write off. It is possible to do experiments from like a comparative psychological standpoint with great apes. It might be controversial to publish or to perform those experiments and stuff like that, but people are definitely doing something along those lines. Like Michael Tomasello obviously comes to mind. And then there's, advances in medical technology, right? Like fMRI and all those sorts of things, but not just those technologies, but also in our ability to process that data with like GPUs and stuff, which maybe you can't necessarily write off all of that stuff. And so it kind of, those sorts of things keep this hemispheric hypothesis chugging along. I would say Iain McGilchrist is like the tip of the spear, as far as the tip of the spear as far as those sorts of things go. But you could compare and contrast him to previous authors in this field. Most notably, I would say Julian Jaynes, right? So with The Origin of Consciousness and the Breakdown of the Bicameral Mind, touches on the same things as Iain McGilchrist, right? There's not only this structural, functional aspect that you're looking at human brains, and then also the evolution of brains, so in a very long time scale, but there's also like a historical, within the last several thousands of years, like what you would say is written history, recorded history. Within those time frames, McGilchrist says that you can look at different periods or regimes of where perhaps maybe the right hemisphere of human populations was more dominant versus the left hemisphere. So he would say that currently we are in an epoch of time where society is dominated by a more like left hemispheric leaning regime. And these are kinds of things that like Julian Jaynes would also talk about. Archaeological things where they're a flip in left or right hemispheric dominance within society. Did that occur maybe when there was the fall of the Roman Empire, right? Are those kinds of things going on? But then, it goes back to how would we know without more evidence, right? So that's what I've been reading. Also, besides that, I've also been reading about the American Constitution. So this guy, I think he's a law professor for constitutional law at Yale, but this is not an academic law school scholarly, it is a scholarly text, but it's not like a serious constitutional law casebook. It's, oh God, it's sitting right here. It's just called America's Constitution by Akhil Reed Amar. I would say it's for maybe like if you were an undergraduate who is in a law adjacent program. So maybe like business, economics, finance, something like that. And then you're going to get sprinkled in a little bit of exposure to law. You might take a class where this would be the kind of book that you would read on the side, in addition to getting all these lectures from this guy, Akhil Reed Amar, right? But I've been reading it because I was thinking that amidst the cultural civil war of the United States and the supposed decline of the American global empire, there's a lot of things that are ultimately philosophically alluding to an existential crisis of what is it that binds together the American people. And it seems to me that the lowest common denominator is the rule of law, which ultimately its bedrock is the American Constitution, which then interacts with, the precedent set by Supreme Court cases and all that kind of history. But it boils down to the American Constitution, because that is something. I'm not the most widely worldly traveled person, but if you go to other foreign countries, besides going to Europe, the rule of law is probably one of the most striking things to Americans going abroad. Is like if you go to Mexico and you wander outside your white middle class tourist resort that's like an extension of Disney World in another country, you go outside that resort, then you're going to be like, oh shoot, the police here are, the way they operate is very different than in America, right? If you go to Thailand or something, or the Philippines, same thing. If you go to the Middle East, Afghanistan, Saudi Arabia, that is different from Mexico or Thailand or America still. So someone who's traveled like that abroad then would come back and would realize what a lot of Americans take for granted, which is the system of rule of law that we live in. Of course, people will criticize that, defund the police, and you can watch police body cam videos that literally go either way of people being dickheads, police being dickheads, but it's like under the court system of the different states which form the United States, people prefer that rule of law to a lot of the other alternatives out there. And so, that's why I was saying like the bedrock that is kind of everyone's common denominator is that rule of law, because so that's why I was like, it's the onus is on me as the supposed intellectual, right? Noam Chomsky, it's the responsibility of the intellectual to not lie, whatever. He says it in his poetic way, of course, because he's Noam Chomsky. But it's like, okay, then if I want to think that I am a part of the culture that was established by the white Anglo-Saxon Puritans living in Massachusetts, then I need to be reading about this stuff. If I want to claim to be a part of the informed electorate that's living in this resurrection of the classical Greco-Roman blah, 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 okay, then I have to read about this stuff. That's where this is going. So, finally, we can get back to a little bit of differential geometry. More rants, though. I'm going to try to keep this to 2 sections. So I'm not going to read like 3 or 4 sections. This is probably going to be a long video with all my ranting. But also in the PDF where I'm at, it's missing like 5 pages from what I'm about to read. So it's going to get dicey anyways. And on the next page, I'm starting on page 179, but then on the next page, turning a page over here, page 181, hopefully I'm going to get a scan of this up on the screen right now. Page 181, figure 70, we've got a hyperbolic paraboloid. Okay, there's figure 68, 69, 70, and 71 are all these different ruled surfaces, okay? And figure 70, hyperbolic paraboloid, just happens to be the cover of this book, okay? The cover of this book is just the colored in version of figure 70. And you know what I was thinking is, I'm not trying to be a schmata salesman. I think it's really low class for someone to kind of like try to do like a pyramid scheme, pump and dump of a YouTube channel with literally no freaking content. Literally some of these YouTubers out here, Your vlogs have literally no content, okay? You can look back at some of my old content and be like, your old stuff has no, it's also empty, just like you're saying right now. Okay, but then those people will sell merch that is so BS and it's crap. And they, you know, they probably only make like $1,000, $2,000 in an entire year, you know, trying to like every single video, they're like, God, buy my merch, guys, which is like, who are you? So I'm not trying to be like that guy, but for like the unity's sake of all you guys out there, my subscribers and stuff, it would be cool if we had some t-shirts, right? And I'm thinking figure 69, the cone, because figure 70 is the cover of this book. I'm not trying to get a RICO case by calling us a gang and putting that out on the internet, but it's like differential geometry gang, and we're gonna have some shirts, figure 69, cone, Anthony makes videos. I'm gonna come up with the design, and I'm probably not gonna make any profit on them. I just want you guys to be walking out there with the figure 69 cone, differential geometry reading stream arc, Anthony makes videos shirts, okay? That's all I'm saying. Also, another thing is the guy who commented on the last video, I don't have it pulled up right now, but on the very last video, the most previous video that I uploaded, a guy commented and said, "You're reading these too fast. I can't follow." That is the comment of the week. Thank you, because that's the kind of feedback that I need on these. And it kind of goes back to me being too mechanical about putting these out there for you guys. Is I'll film these, I'll talk as fast as I can, and then I just chop out all of the dead air, even in between sentences, which is probably not good. You know, it's one thing to cut out when I'm breathing in or when I mess up or anything like that, but sometimes when I'm reading these sentences, I forget that there's like a place for actually leaving in natural pauses or little gaps so that other people listening to me talk can process and understand what I'm saying. It also undermines my own credibility when I'm speaking too fast, because then it seems like I'm trying to deceive other people by speaking so fast that other people can't get a word in edgewise. That could be a strategy of someone who's trying to manipulatively be like, oh, I'm just gonna pull the wool over your eyes. So in an effort to be more credible, I'm gonna slow this one down a little bit. Anyways, section 58, ruled surfaces and developable surfaces. The problem of finding surfaces isometric to a plane is of special importance. We will prove in section 59, the next section, that a surface can be brought into isometric correspondence with a plane if and only if it is a developable surface. As a preparation for this, we now introduce the concept of a ruled surface and of a developable surface. A surface is called a ruled surface if it contains at least one parameter family of straight lines which can be chosen as coordinate curves on the surface. These straight lines are called generators of the ruled surface, not to be confused with, for example, the generators of an algebraic group. Consequently, a ruled surface may be generated by a continuous motion of a straight line in space. I'm going to go and I'm going to Facebook Live, or not Facebook Live, I'm going to YouTube Live this. Because this is what the people want. Such a motion is completely determined if the path vector y of s, where s is arc length, of course, as it has been throughout this book, of a point of the moving line is given, and also the direction of the line for every value of s. For example, by a unit vector z of s. A ruled surface may therefore be represented in the form vector x in terms of s and t as parameters, which is equal to then the vector y in terms of s plus parameter t times the vector z of s, where in this case, y dot, or the first derivative with respect to arc length of the vector y, cross product with the vector z is non-zero. Obviously, the coordinate t is the directed distance of the points of this surface from the curve vector y of s measured along the corresponding generator. In order that this representation of vector x in terms of s and t represent a surface, the vectors x sub s, which is equivalent to partial x partial s, and vector x sub t, which is equivalent to partial x partial t, must be linearly independent for every value of s. The curve y of s is known as the directrix of the ruled surface. Clearly, one may choose as directrix any curve on the surface which intersects every generator exactly once and at an angle different from 0. S may also be replaced by any other allowable parameter of the directrix. If the unit vector z undergoes a translation and becomes bound at the origin capital O of the Cartesian coordinate system in space, then it generates a curve on the unit sphere with center capital O. This curve is called the spherical indicatrix of the ruled surface. Obviously, the spherical indicatrix depends on the geometric shape of the ruled surface only, but is independent of the special choice of the directrix. It may therefore sometimes be advantageous to choose the arc length of the spherical indicatrix as one of the coordinates on the ruled surface. But in doing so, we exclude cylinders, since for these surfaces the vector z is constant and the spherical indicatrix therefore degenerates into a point. All right. And I will say at this point, this is a flashback to now section 17, which is like 140 pages ago, where they brought up the tangent indicatrix, the principal normal indicatrix, and the binormal indicatrix. So those are all infinitesimal projections on the unit sphere, if I'm not mistaken. So it's like things like ds sub t squared equals, or ds sub p squared equals, and then it gives you these things that are in terms of curvature and torsion. This spherical indicatrix is kind of like similar in that it's a projection onto one of these surfaces, right? Depending on the choice of the vectors y and z, one may obtain different types of ruled surfaces. Let us mention some examples. If z equal to z naught is a constant vector, we have a cylinder. If z equal to a fraction where in the numerator we have c naught minus y, where both are vectors, over a denominator which is the absolute value of c naught minus y, then the ruled surface, which was previously given in the form as x in terms of s and t previously, is a cone with apex at the point c naught. To every twisted curve of class r greater than or equal to 2 with positive curvature, we can associate 3 ruled surfaces by taking for z the unit tangent vector t, the unit principal normal vector p, and the unit binormal vector b, respectively. In this manner, we obtain the tangent surface, which is a vector x in terms of s and t, such that we have the vector y in terms of s plus the parameter t times the vector t in terms of s. Similarly, we have the principal normal surface, where if given in terms of a vector x with parameters s and t, this would be the vector y of s plus the parameter t, then times vector p in terms of s. And finally, we have the binormal surface, which given as a vector x in terms of parameters s and t, would be the vector y in terms of s plus parameter t times the binormal vector b in terms of arc length s, respectively of the curve y of s. Other ruled surfaces are the right conoid, for which referred to problem 28.2, the hyperbolic paraboloid, which is given by x1 squared over a squared minus x2 squared over b squared, then minus x3, which is equal to 0, and the hyperboloid of one sheet, which is x1 squared over a squared plus x2 squared over b squared minus x3 squared over c squared, which is equal to 1. The last two surfaces are such that through every point, there pass two straight lines which lie on the surface. Oh, I feel like people are probably leaving this. I've seen like a few people jump on and then off. It's probably because they can't actually see what I'm reading. That's why it's behind the scenes. Anyways, a developable surface is a special ruled surface with the property that it has the same tangent plane at all points on one and the same generator. And now we are at theorem 58.1. A ruled surface, which is a vector x in terms of parameters s and t, which is given by vector y of s, which is a curve, then plus parameter t times vector z of s, is a developable surface if and only if the determinant, which column-wise is given by y dot, then z dot, where y dot and z dot respectively are the first derivatives of vectors y and z in terms of arc length s, this determinant is then equal to 0. The proof is as follows. Let capital P1 and capital P2 be 2 points of an arbitrary fixed generator corresponding to the particular arc length S naught, and let P1 and P2 correspond to the respective values T1 and T2. If the ruled surface is a developable surface, then, by definition, its tangent planes at P1 and P2 coincide. Those planes are spanned by the vectors vector x sub s in terms of the particular arc length s naught, so evaluated at the particular arc length s naught, and the particular value of the coordinate t, which is t1, then this is equal to y dot evaluated at that particular arc length s naught plus the particular value of the parameter t, which is t1, then times the vector z dot at s naught. Similarly, we have vector x sub s at s naught, but then at t2 this time, which is equal to y dot at s naught plus t2 times z dot at s naught. And finally, we have the vector x sub t evaluated at s naught and t1, which is the same as x sub t being evaluated at s naught and t2, which is equal to z evaluated at the particular arc length s naught. Hence, those three vectors must be linearly dependent, so the determinant where column-wise, in the first column we have y dot plus t1 times z dot, and then in the second column we have y dot plus t2 times z dot, and then in the third column we have z, this entire determinant is equal to 0 because these three vectors are linearly dependent. Applying to this determinant the elementary rules of calculus of determinants, we thus obtain the determinant above in the statement of the theorem. So yeah, that was pretty straightforward, I guess. Conversely, starting from the determinant in the statement of the theorem, we find the above relation from which the coincidence of the tangent planes of the arbitrary points P1, P2 on the same generator follows. We next consider the three special ruled surfaces, the tangent surface, the principal normal surface, and the binormal surface, associated to a given curve y of s with positive curvature. And we come to theorem 58.2. The tangent surface is always a developable surface. The principal normal surface and the binormal surface are developable surfaces if and only if the corresponding curve is plane. The proof is as follows. In the case of the tangent surface, we have that the vector z is equal to the vector t, which is equal to the vector y dot, for which refer to the expression for the tangent surface. The determinant from the statement of theorem 58.1, namely the determinant of y dot z and then z dot being equal to 0, vanishes since two columns are equal. In the case of the principal normal surface, we have from the expression for the principal normal surface and from the determinant in the statement of theorem 58.1, we have from these that the determinant column-wise of y dot z and then z dot is now equal to the determinant column-wise of y dot p and then p dot for the principal normal vector. And this is then equal to column-wise y dot, then in the next column p, and then in the next column we have the quantity negative kappa times y dot plus tau times b closed quantity. And this determinant is then equal to the determinant column-wise of y dot, then p, then tau times b. And this is due to the formulae of Frenet. Since the three vectors y dot, p, and b of the trihedron of the curve are linearly independent, this determinant is 0 if and only if tau is equivalent to 0, so if torsion is 0. That is, if and only if the vector parametric representation y of s is a plane curve. If, conversely, this vector parametric representation y of s is a plane curve, the principal normal lies in the plane of the curve. The principal normal surface, therefore, is a plane. In the case of the binormal surface, we have that the determinant column-wise of y dot z and then z dot is equal to the determinant column-wise of y dot, then b dot, which is then equal to a determinant column-wise of y dot, then b, then of negative tau times the vector p. And this determinant is 0 if and only if tau torsion is 0. That is, if and only if the vector parametric representation y of s is a plane curve. Conversely, if the vector y in terms of arc length s is a plane curve, then the vector binormal is constant. Hence, b dot is equal to 0, and therefore also the determinant column-wise y dot, then b dot is equal to 0. So, this binormal vector b generates a cylinder which intersects the plane of the vector parametric representation y of s along this curve. In order that the tangents to a curve y of s generate a surface capital T, the vectors given by x sub s, which is equal to y dot plus the parameter t times the vector y double dot, and the vector x sub t, which is equal to the vector y dot, these vectors must be linearly independent. Now, the magnitude of y double dot is equal to kappa, which is equal to curvature, for which we can refer back to section 12 on curvature. Hence, those vectors are linearly independent if and only if kappa is non-zero, but only at points for which t is non-zero. Along the curve with a vector parametric representation y of s, but such that t equals 0, and this is for the expression of the tangent surface as given previously, is never allowable. The curve y of s is called the edge of regression of its tangent surface capital T. The tangent surface consists of two sheets corresponding to values where t is greater than or equal to 0 and t is less than or equal to 0, respectively, which have the curve y of s in common. The fact that the expression for the tangent surface as given previously is not allowable at the points of y of s is therefore a consequence of the geometric shape of the surface capital T and does not result from the special choice of the representation. So figure 28, which is on page 65, which is of a circular helix C and the tangent surface of capital C and an involute capital E. This is going back to section 22 on involutes and evolutes. It's like, some of those sections in chapter 1, they're on topics which if you go to a different differential geometry book like the Kuhnel book, you won't find those topics as like outright sections within the corresponding chapters. But then you'll find them maybe like tucked away in the problems at the end of those sections. But here we are in section 58, and then, stuff gets recalled back to the surface. Anyways, so figure 28 shows the tangent surface of the circular helix. If the curve is plane, the two sheets of the corresponding tangent surface coincide and lie in the plane of the curve. We still have a ways to go. In order to prove all those facts, we choose an arbitrary point, capital P naught, of the vector parametric representation y of s, at which kappa naught is positive and tau naught is non-zero. So that is to say we have positive curvature and non-zero torsion at this arbitrary point, and take as x1, x2, and x3 axes of a Cartesian coordinate system the tangent, principal normal, and binormal, respectively, of this vector parametric representation y of s at this arbitrary point, capital P naught. Then, in consequence of the canonical representation, for which refer back to section 18, the components y1, y2, and y3 of the position vector y of s take the form y1 is equal to s minus kappa naught squared over 6, then times s cubed plus etc. Then y2 is equal to kappa naught over 2, then times s squared plus kappa naught dot, so I guess the first representation, the first derivative with respect to arc length of kappa naught, so that's what kappa naught dot is, over 6, then times s cubed plus etc. y3 is equal to kappa naught times tau naught all over 6 times s cubed plus etc. Where the index 0 denotes the value of the corresponding quantity at capital P naught and the value s equals 0 corresponds to capital P naught. If we differentiate this representation with respect to arc length s, we obtain the components of the tangent vector y dot of s. In consequence of the representation for the tangent surface previously given, we thus have x1 in terms of parameters s and t, which is equal to s minus kappa naught squared over 6, then times s cubed plus terms, etc., plus then finally the parameter t times the quantity 1 minus kappa naught squared over 2, then times s squared plus terms, etc., closed quantity. Similarly, we have x2 in terms of parameters s and t, which is equal to kappa naught over 2, then times s squared plus kappa naught dot over 6, then times s cubed, plus terms, etc., then plus parameter t times quantity kappa naught times s, plus kappa naught dot over 2, then times s squared plus terms, etc., closed quantity. And similarly, we have x3 in terms of parameters s and t, which is equal to kappa naught times tau naught over 6, then times s cubed plus terms, etc., then plus, finally, parameter t times quantity kappa naught times tau naught all over 2, then times s squared plus terms, etc. We now determine the curve of intersection of the surface capital T and the normal plane capital N of the curve with a vector parametric representation y of s at the arbitrary point capital P naught. Capital N is given by the equation x1 equals 0. Hence, from the first of the three expressions previously given, for x1, x2, and x3, we thus obtain that t is equal to the negative fraction with a numerator of s minus 1/6 times kappa naught squared times s cubed plus etc. all over a denominator of 1 minus 1/2 times kappa naught squared times s squared plus terms, etc. This is then equal to negative s minus kappa naught squared over 3, then times s cubed plus etc. If we insert this into the other two expressions of these x1, x2, and x3, we find the following representation of the curve of intersection of capital T and capital N. x2 is equal to negative kappa naught over 2, then times s squared plus etc. And x3 is equal to negative kappa naught times tau naught over 3, then times s cubed plus etc. terms. If we neglect the terms indicated by dots, we have a semi-cubical parabola with a cusp at the arbitrary point capital P naught, for which referred to figure 72 above. The tangent surface capital T thus consists of two sheets, which have the curve y of s in common, and y of s is the edge of regression, as was stated above. Any developable surface may be characterized as follows. And now we come to theorem 58.3. Every developable surface x of s and t, for which refer back to the expression for the tangent surface previously given, can be subdivided into sufficiently small suitable s intervals so that the portion of the surface corresponding to any of these intervals is a portion of either a plane, a cylinder, a cone, or a tangent surface. The proof is as follows. If the expression for the tangent surface as previously given is a developable surface, then the determinant from theorem 58.1, namely column-wise the determinant y dot then z dot, which is then equal to 0, that determinant being equal to 0 holds. That is, there are three functions, namely c of s, d of s, and e of s, not all 0 for any value of s, such that c times vector y dot plus d times vector z plus e times vector z dot is equal to the vector 0. We may assume the functions c, d, and e to be of class R, that is, it is at least R times differentiable, as well as R minus 1 on down to 0, I guess, if y dot and z dot are of that class. Case 1. If c of s is equal to 0 for all values of s in an interval capital I such that s is greater than s naught but less than s1, so s is greater than s naught but s is also less than s1, then in that interval capital I, then d times vector z plus e times vector z dot is equal to the vector 0, where at every point of the interval capital I, at least one of the functions d and e is different from 0. Since the vector z is a unit vector, then the scalar product of z with itself, or z dot z, which I don't like saying that because of how many dot derivatives are used here, so the scalar product of z with itself is equal to 1. And therefore, the scalar product with z and z dot is equal to 0. So this previously stated relation of d times vector z plus e times the vector z dot being equal to the vector 0 can be satisfied if and only if the vector z dot is equal to the vector 0, that is, the vector z is constant. Hence, in this case, we have a portion of a plane or of a cylinder. Case 2. If c of s is non-zero in an interval capital I prime, namely where s is greater than s2, but s is also less than s3, then the previous relation where c times the vector y dot plus d times the vector z plus e times the vector z dot is equal to the vector 0, that can be written in the form where vector y dot is equal to alpha times vector z plus beta times the vector z dot, where alpha is equivalent to negative d over c and beta is equivalent to negative e over c. We set vector y equal to vector y star plus beta times vector z, that is to say where the vector y star in this case is equal to the vector y minus beta times the vector z. So if you're not following what just happened there, we have the vector y equal to the vector y plus beta times z minus beta times z, and then we just call y star the vector y minus beta times the vector z. Differentiating this expression with respect to arc length s and taking into account the previously given relation for the vector y dot in terms of z and z dot with coefficients alpha and beta, which are in terms of those functions e, d, and c, we then find that the vector y star dot is equal to vector y dot minus beta times the vector z dot minus beta dot times the vector z, which is then equal to capital A times the vector z, where capital A is equal to alpha minus beta dot. Case 2a. If capital A is equal to 0 in the interval capital I prime, then the vector y star dot is equal to the vector 0. Hence, the vector y star is equal to y star naught, which is equal to a constant. And consequently, the expression for the tangent surface is then in the form of the vector x, which is equal to the vector y star naught, plus the quantity t plus beta, closed quantity, times the vector z. This is a portion of a cone or of a plane. Case 2b, or not to be. Horrible. If, however, capital A is non-zero in a subinterval capital I double prime of the interval capital I prime, then in consequence of the previously given relation in case 2 for y star dot, then in capital I double prime, the vector z is equal to the vector y star dot over capital A. And therefore, by the relation for y in terms of y star, where we did y equals y plus beta times z minus beta times z, by means of that, we now have that the vector x is equal to the vector y plus t times the vector z, which is equal to the vector y star plus v times the vector y star dot, where v, in this case, is equal to the quantity t plus beta, closed quantity, all over capital A. Thus, in this case, the vector parametric representation x in terms of parameters s and t is a portion of the tangent surface of the curve y star of s. Developable surfaces are of particular importance because they're the only surfaces which can be mapped isometrically into a plane, as will be seen in the following section. Problem 58.1. Find an analytic expression of the Gaussian curvature of a ruled surface and prove that a ruled surface is a developable surface if and only if its Gaussian curvature vanishes. The solution of problem 58.1 is as follows. Using the expression for the tangent surface, which is x of s is equal to y of s plus parameter t times vector t of s, we have that the vector x sub s is equal to the vector y dot plus t times the vector z dot. We have that the vector x sub t is equal to the vector z. And since s is the arc length of the curve with a vector parametric representation y of s and z is a unit vector, first we have the components for the first fundamental form. Namely, we have g sub 1, 1 equivalent to the scalar product of x sub s with itself, which is equal to then 1 plus 2t times the scalar product of y dot with z dot, then plus t squared times the scalar product of z dot with itself. Then we have g sub 1, 2, which is equivalent to the scalar product of the vector x sub s with the vector x sub t, which is then equal to the scalar product of the vector y dot with the vector z. And finally, we have the component g sub 2, 2 being equivalent to the scalar product of the vector x sub t with itself being equal to 1, since z is a unit vector. So the discriminant of the first fundamental form, g, is equal to 1 plus 2t times the scalar product of y dot with z dot plus t squared times the scalar product of z dot with itself, then minus the quantity of the scalar product of y dot with z, closed quantity squared. Hence, from the expression for the unit normal vector to a surface capital S at a point capital P, namely that the vector n is equal to, in the numerator, the cross product of vector x sub 1 with vector x sub 2 all over a denominator of the magnitude of the cross product of the vector x sub 1 with the vector x sub 2, which is equal to, in the numerator, the cross product of vectors x sub 1 with vector x sub 2 all over a denominator of the positive square root of the discriminant of the first fundamental form, all over the square root of g, the discriminant of the first fundamental form, which is equal to 1 over the square root of g, then times the quantity, which is the cross product of y dot with z, then plus t times the cross product of z dot with z. Close all quantities. Since the vector x sub t is equal to the vector 0 and also b sub 2, this is a component of the second fundamental form, b sub 2 is equal to the scalar product of x sub t with the vector n, this is equal to 0, for which we can refer to the definition of the coefficients of the second fundamental form. Since the vector x sub st is equal to z dot, we obtain that capital K, this is the Gaussian curvature, is equal to b over g, where b is the discriminant of the second fundamental form and g is the discriminant of the first fundamental form. This b over g is equal to the negative quantity, where we have a fraction in the numerator is the determinant column-wise of y dot, z, and then z dot, that's the determinant, all over g, which is the discriminant of the first fundamental form. That fraction contained within the quantity, so closed quantity, is then squared. So you have this fraction, which is the determinant, y dot, z, z dot, all over g, which is the discriminant of the first fundamental form. Take that, square it, and then negate it. Flip the sign, that is capital K, the Gaussian curvature. Okay, capital K vanishes if and only if something is satisfied. Not me. Only if this determinant from the statement of theorem 58.1, where we have y dot, z, z dot, determinant is equal to 0, capital K vanishes if and only if that is satisfied. And that is the end of the solution for problem 58.1. So now, holy smokes. All right, here we go. 1, 2, 3, 4. Whew, got this. Yeah, because now this is getting into, there's going to be all that third fundamental form stuff. So I'm going to have to review or talk about the first and second fundamental forms before I do this. I've already been on here for an hour. And I should go over the references. Euler, Gaspar Monge, O. Rodriguez, and Gauss. I'm probably not going to go live for that. Maybe I will. Holy smokes. I gotta edit this crap.